Hi, welcome to the next video. In this video we will cover concepts about capacitors. Uh, so capacitors are devices which can store electric charges. Uh, for example, a dam can store a potential if a dam raises the level of water, and that has potential energy in it which can do work for us, for example can generate electricity. Similarly, if we can store electric, or we can generate an electric field in a region, that region will have potential energy and it will have capacity to do work. How energy an electric field has a potential energy, that can be estimated uh, by if we know that whenever there is an electric field, we studied in last video, there is a potential electric potential also associated with that, and what electric potential is nothing but energy per unit charge. That is one way of understanding how electric field has an intrinsic energy into it. Another way we will study as we progress into this topic of capacitors. But capacitors, in general, there are many types of capacitors. One which has one which are showing in a simple Google image search, where two plates are there mounted parallel to each other, and they have the property to store charges, and because of that, those stored charges, it has an electric field inside it, and because it has an electric field inside it, it has some energy stored inside it, which can be used at a later stage to extract work from it. So let us quickly jump into some of the basic concepts how capacitors can store charges. uh, so here is one simple figure where there are two parallel metal plates. Right now there is no material inside that, but later on we will also study what happens when there is a material inside this. But whenever there are two parallel plates, or maybe we'll as we'll see later, two cylinders or two spheres, metal cylinders or spheres, when they are kept close to each other, they gain a potential to store charges. uh, so let us see why they gain the capability of store charges to store energy when they are kept at each other, close to each other. So consider this figure where two parallel plates, these parallel plates uh, can be like these parallel plates here, which are metal, or another view you can see here. But from cross sectional view, you will see two parallel plates like this, and they are connected to a battery. So so when I connect these to a battery has a positive terminal and a negative terminal. So electrons flow from this negative terminal to this plate, and so this plate becomes negatively charged, and electrons flow away from this plate. But now, because this is a negatively charged plate, uh, there will be a induced positive charge on this plate. Now the reason for positive charge induction at this place, you can consider 2-3 reasons why, through which you can justify a positive charge here. First reason is which is a little tough to comprehend, is inside the metal there must be a zero potential. So in order to have zero potential or zero electric field inside a metal, to counteract the negative charge which is here in the surrounding region, here the surrounding region, so to counteract that, there will be a positive charge induced here. That is one way to think about it. Another way to think about it is, uh, if I have a negative charge here, and I know that a metal has free electrons which can move freely among freely with each other, those negative charge, those free electrons, because there is a negative charge here, they will be repelled against this negative charge here. So they go through this wire because they are being repelled. They are going to this positive terminal of the battery. That is another way to think about it. So overall, the gist is, whenever I connect two plates to the battery, a positive charge will be induced here and a negative charge will be induced here. So now when I remove these wires, when I disconnect the battery from it, still the positive charge and negative charge will still be there, because there is no path. When I disconnect these wires, there is no path where these charges, induced charges, can go. So whenever I take out this capacitor, it has still those, I have those stored charges which are positive here and negative here, and I can later on connect them, say through a bulb or through a flashlight of a camera, to extract that amount of to make the charge flow or make a current flow and extract some amount of work through it. So this is the basic overview of how we use a capacitor, the basic working principle of a capacitor. And let us now go and discuss a little more detail about some of how we quantify the amount of charge and what are the various properties. Okay, now we have, what I have shown here is the capacitors, which are one parallel plate capacitor which is connected to a battery. So this is the positive terminal of the battery, this is the negative terminal of the battery. So here a positive charge Q will flow in, so plus Q. There will be a minus charge here, which we just discussed, and let me give a potential V. So the amount of charge which can go in, charge cannot indefinitely go in, and there is one option, the charge can indefinitely go in from this battery to this battery to this terminal, but that is not the case. After some time the charge flow stops, and the amount of charge which is finally stored inside the capacitor given enough time will be directly proportional to the potential which we apply. So Q, the amount of charge which the capacitor has will be storing, will directly be proportional to the potential difference which we have applied onto this between these capacitors, plates of the capacitor. And because there is a proportionality sign, we obviously will have a, when we put an equal to sign to it, there will be a constant of proportionality, Q is equal to CV. So the charge which is stored inside a capacitor is directly proportional to a quantity, the proportionality constant C, and the potential difference applied across this capacitor. So now this proportionality constant is known as capacitance of the capacitor. So the proportionality constant C is known as the capacitance of the capacitor, and it is obvious that more the value of C, the more charge it can store. So the amount of charge which a capacitor can store is directly proportional to the capacitance or C value of the capacitor. Now what the two questions arises. One is, what is the on what values do the, on what factors do the C value depend on, or does the C value depend? And the next question is, how to find that value of C? So the answer of first question is the value of C depends on the geometry and type of the capacitor. Okay, so the C value will be different if I have a parallel plate capacitor like this. So parallel plate capacitor, or there are capacitors which are cylindrical capacitors. So instead of these parallel plates which are so these parallel plates will be somewhat like this, but instead of parallel plates I can have cylinders. So two cylinders are there inside, or one cylinder inside another cylinder. On one I can give a positive charge and the other I can give a negative charge. Here also, like the inner cylinder I can connect to a positive terminal of the battery, and the outer cylinder I can connect to a negative terminal of the battery. This is one type of capacitor which is called cylindrical capacitor. Another type of capacitor which can be called a spherical capacitor. Where two spheres are there, so these are 3D spheres, spherical shells, one inside the other. One of the shell I can connect to a positive terminal of the battery, another I can connect to a negative terminal of the battery. So here plus positive charges will be stored here, and in the outside negative charges will be stored here. So this is called spherical capacitor. So the value of C, or the capacity to contain the charges, capacitance is nothing but the capacity to hold the charge. More the capacitance, more charge holding ability the capacitor has. So for the value of C will depend on the type of the capacitor, whether it is a parallel plate capacitor, a cylindrical capacitor, or a spherical capacitor, and also on the geometry of the capacitors. For example, if I have two parallel plate capacitors, but they are separated by different amount, or they have different surface areas, then they will have different capacitance or the ability to hold the charges. So in the next section we will discuss how to find the capacitance of any given configuration of capacitor. Not specifically we will derive the capacitance of a parallel plate capacitor, cylindrical capacitor, and a spherical capacitor. So the first and easiest way, the first will be, we will derive what is the capacitance of a parallel plate capacitor. So these parallel plate capacitors will look something like this, and they will be connected to a battery, and we will find the capacitor of a capacitance of a first we will find of a parallel plate capacitor, then a cylindrical, and then a spherical. So before I do that, I will give you a general methodology how to calculate the capacitance of a capacitor, and with that general methodology what you can do is you will be able to we'll apply the same methodology to a parallel plate capacitor to find its capacitance. We will apply the same methodology to a spherical capacitor, and we will apply the same methodology to a cylindrical capacitor. So I will just give a methodology, and the rest will be very easy if we apply this methodology. So first step will be to give a charge Q. Give a charge Q, or assume a charge Q. Assume a charge Q. So we will first assume that there we have, because of this there has been a charge Q which has gone to the capacitor. Second step is applying Gauss law. Applying Gauss law, find the electric field generated. Find the So whenever there is a plus charge here and a minus charge here, there will be an electric field which gets excuse me, which gets generated, and the direction of that electric field is from the positive charge to the negative charge, which we already know. So whenever we give a plus charge and a minus charge on to a capacitor, there will be an electric field generated between the plus charge and minus charge, and that is the reason, because there is an electric field set up between the capacitors, that's the reason why it has a potential energy and it has a capacity to do work. So the methodology to find the capacitance is, applying Gauss law, we have to find the electric field set up inside the capacitor. Now so Gauss law, what is the Gauss law? Gauss law is integration of E ds, surface integral of E ds is equal to Q in by epsilon naught. So if we assume a charge inside the capacitor, then we'll, with that assumed charge, and if you use this Gauss formula, we can find what is the electric field. So once we find that electric field, the next step is, as I was discussing, if there is an electric field, then there will be an electrical potential energy inside that field. So what is the formula for that potential difference? So next will be V, or potential difference, or I can write dV. Potential difference will be equal to integration, or the general notation is V final minus V initial. Generally V initial will be 0, will be equal to, how do I find the potential difference between this and this? If I know the electric field, so from the last chapters, it is nothing but integral of E dot ds. So path integral of E dot ds from that initial to final position will give us the potential difference. And the fourth step is, now I have found out what is V, the potential difference between this and this, and I know what is my given charge Q. So capacitance will be equal to, just we discussed the concept, Q is equal to CV. So capacitance C will be equal to Q by V. So this is the general methodology which we will apply in the case of parallel plate capacitor, in place of which will be applied to parallel plate capacitor, which will apply to cylindrical capacitor, which will apply to spherical capacitor. All capacitors, to find the capacitance, we will apply this general methodology. Give a charge Q, find E applying Gauss law, with E find the potential difference with that E, and when you find the potential difference, then with the formula C is equal to Q by V, we will find the what is the capacitance of the capacitor. So now let's start deriving the capacitance of different capacitor configuration one by one. So first I will derive for the parallel plate capacitor. So this is the these are two parallel plates. Okay, one has been given positive charge and one negative charge. So of that methodology, first thing is give a charge Q. Give a charge Q. So we will assume that a charge Q has flown to this, a charge of minus Q has flown into this. Now the second step of that methodology, so first is we have given a charge Q. So we have given a charge Q. Second is find the value of E, find E, okay, applying Gauss law. So if you go to the derivations, we had a chapter called Gauss law derivations, and in that we derived that if I give a charge of Q on a metallic plate, what is the electric field setup? If you use that formula, we will get the directly get the value of E, but still for completeness sake, we will let us do this again. So this is the electric, or let me take a cross section like this. This is the cross section of my parallel plate capacitor. I have given a charge Q, or I have given a charge Q. This surface has a charge Q inside it. Remember, all the charges on a metal are on the surface only, and I want to find what is the electric field because of this charge Q. So find E applying Gauss law. So for applying Gauss law, we have to make a Gaussian surface. So let me make a Gaussian surface. So the cross section of that Gaussian surface will be like this. So our Gauss law says that E ds is equal to Q in by epsilon naught. So inside the right hand side, Q inside this Gaussian surface, excuse me, there is a charge Q inside this Gaussian surface. So this becomes, right hand side becomes directly Q by epsilon naught, and left hand side, because this is a symmetrical surface, all this E, there is a same E throughout, which is flowing out throughout this Gaussian surface. Inside the inside this plate there is no electric field, the only electric field is outside this plate, and so E is a constant. E will come out in E integration of ds, and ds, if you remember, ds is the integration of the surface area. So the surface area of a parallel plate capacitor is nothing but the length times the breadth. So L into B is the area of this. So which is integral ds is nothing but the area. So E into area is equal to Q by epsilon naught. Integration of ds is nothing but the area of the square plate, and so from this we get E is equal to Q by epsilon naught A. So if you remember from the Gauss law derivation, electric field due to a metallic plate was sigma by epsilon naught, or due to a metallic plate, and sigma is nothing but Q by A. So that's what exactly what we got. We basically did this derivation again. So step 2 is complete. We have found out E using Gauss law. So E is equal to Q by epsilon naught A. The step 3, if you remember, the step 3 was find the potential difference between these two plates. Now there is an electric field E between these two plates, which is equal to Q by epsilon naught A, and suppose that the distance between these plates is D. Okay. So using Gauss law, now we have to find what is the potential difference between these two plates. Not Gauss law, using the normal potential formula, which is V is equal to integration E ds. Okay. So E comes out, sorry, here it is integration E dx. Okay, let me assume this is x direction. So E dx is the potential difference between this plate and this plate. E comes out integration of dx. So V is equal to integration of E dx. and addition of all the small distance dx, 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 dx is nothing but the total distance between these two plates. So, this I can write V is equal to E, integration of dx is ed. So, V is equal to, if I substitute the value of E from this equation, it is Q epsilon naught A by D into D. So, E is Q by epsilon naught A times D. Now, the fourth step is find C using the formula Q by V. So, if I substitute the value of V from here in here, I will get C is equal to epsilon naught A by D. So, see, the value of capacitance of a parallel plate capacitor depends on the area of each plate. Area can be length into depth of each plate divided by the distance between these each plate. So, again the capacitance of a parallel plate capacitor depends on the geometrical parameter of these parallel plate capacitor, which is again depends on area of each plate, not the combined area of two plates, but area of each plate. A is the area of each plate or area of one plate divided by D is the distance between the plates. So, this is the derivation of the capacitance of a parallel plate capacitor. Now, let us go on to derive the capacitance of a cylindrical capacitor. So, I have one cylinder here, and I have another cylinder okay. So, I have one cylinder here and I have another smaller cylinder, say here, and so maybe I give a positive charge. It doesn't matter which cylinder you give a positive charge, because they will be, again I am having some problem with, so I connect this to a positive terminal and this to outside to a negative terminal. So, first step to find the capacitance of this capacitor is step number 1, which we discussed, was give a charge Q. So, we will give a positive charge plus Q here throughout. Again remember, this is a metal, so all the charges will be on the surface, and we give a minus charge onto the minus charge onto the surface, which is equal to Q. So, you give a Q charge here and minus Q charge here. Next step is to calculate the, so when I give the charges, electric field will be set up. So, electric field will be set up between these two, and in a 3-dimensional look it will be something like this. So, electric field will be set up throughout this internal cylinder, and we have to find the electric field using the Gauss law. So, in order to use Gauss law, let me make another a Gaussian surface, which is a cylindrical surface. between these two, this Gaussian surface is at a distance, or it is at the radius of that Gaussian surface is r naught r, and let me say that the inner radius is r in, and the outer radius is of the outer cylinder is r out. This is an important parameter. This defines the geometry of the cylindrical capacitor on which the capacitance will finally depend. So I have made a Gaussian surface which is in a blue line. So that Gaussian surface is also a cylindrical surface, and the Gauss law is integration of E dot ds is equal to q inside. So inside charge is within this Gaussian surface is what is inside this inner cylinder, which we have assumed to be q. So q by epsilon naught. Again E will be, because it is a symmetrical situation throughout this Gaussian surface, each point in the cylinder is equidistant from have the same distance from the inner circle as well as the outer circle. So this is a symmetrical situation. E will be same throughout this Gaussian surface. So E will be a constant throughout the Gaussian surface, and I can take out this E just because of the nature of the symmetrical problem. I can easily say that E will be same throughout this Gaussian cylinder, and the direction I have shown in the green lines. So E ds will be equal to q in by epsilon naught. Again ds is the total surface area of the Gaussian cylinder, and which is equal to, so the total surface area of any cylinder is so E into integration of ds, which is the total surface area of this cylinder, which is equal to 2 pi r into L. R is the radius of this Gaussian surface, and L is the height of the cylinder or length of the cylinder. This is equal to q by epsilon naught. So E is equal to q by 2 pi r L epsilon naught. So we have completed the second step using our Gauss law. We have found out what is the electric field inside this, and the third step, we can now go to the third step, which was what is the potential because of this electric field. So we will use the same formula, only thing is now we are dealing with radial coordinates. So we are now in radial coordinate system. So V will be integral of E dr. If you remember the formula, there is a negative sign here. So V will be equal to E dr, which is equal to, now if I substitute the value of E, it is equal to minus q by 2 pi r L epsilon naught dr. So if you see, now there is a r term here, so all the constants will come out. So minus, now r varies from what to what. So r varies from the inner cylinder. The electric field is, we are finding the potential difference between this inner cylinder and the outer cylinder. So r varies from inner cylinder from r in to r out. Electric field is in this region. So potential difference exists between this region. So the r varies from the value of r in to r out in this region. So we have to go from the inside diameter of the cylinder to the outside diameter. So it varies from r in, we have to integrate from r in to r out. So this becomes, if we take out the constant of integration, it becomes minus q by 2 pi r L integration dr by r, which is equal to uh, r in by r out. And if we remember the basic formulas for integration, uh, integration of dr by r is nothing but ln of r. So ln of r from r in to r out, the final formula with this, if we consider the negative sign also, I will not work out those details, but the final value, which is just a simple definite integral which can be easily evaluated, it will be ln of r out by r in. Sometimes some textbook will have r out as b and r in as a, so it will be q by 2 pi rl ln of b by a, or but you get the idea. It is basically ln of the outside cylinder radius divided by the inside cylinder radius. And finally, the fourth step is will be finding C. C is equal to Q by V, and if I replace the value of V from here in here, I will get C is equal to 2 pi epsilon naught L by ln of R out by R in. So again, the capacitance is dependent on the length of the cylinder, the outside radius of the cylinders and the inside radius of the cylinder, and it depends, again it depends on the geometrical parameter of the cylinders. So I think we have time up to cover up till this in this video. In the next video, we will continue to find out the capacitance, apply the same methodology to find out the capacitance of a spherical capacitor, and also discuss some of the other concepts with capacitors. So see you in the next video.